So undergraduate calculus or AP calculus is usually the first time that students are introduced to the concept or the mathematics of optimization. And I think optimization problems are probably the hardest part of calculus. That's what makes calculus hard, is the optimization type problems. And I think the reason that they're really difficult is that you have to extract information and relationships among the variables that you are given, kind of from either a set of initial conditions or from a prompt. And that process is very difficult and just requires an absurd amount of work to do that. In addition to that, I think one of the hard things about it is that not a lot of people, I think, use methodical approaches. And so I've gone ahead and gonna try my best to come up with a methodical approach, and here's what I've gotten so far. The first thing you want to do is look at the equation to find the critical value or the critical variable, or in this case, look at what you're given, the information, the initial conditions, right? All that stuff. The next thing you want to do is you want to look at your parameters, at your initial conditions or whatever it is that you're given. And this is the hard part. Extract as much information in unknown relationships as possible. Step 3 is pretty straightforward. You want to set up your equation or your parameter, and you want to express that as a single variable, x, y, theta, whatever. And then the last step is really just the same way that you do any type of problems of optimization, which is derive for the maximum and then for the minimum. Okay, so let's just go ahead and go through this. This is only a mathematician would come up with a question like this. But basically, you have a sheet of paper here that is folded across, and we're trying to figure out what the value for x, for that fold increase there, or for that fold point, is going to make L, the crease here, as small as possible. Okay, so going off the first thing here, look at our equation, find our critical value. We want to know what value for x makes L as small as possible. Now you probably want to look at our parameters that we can have here. So just from looking at this, what are all the different types of relationships that we can deduce from that? What are all the relationships maybe that we can extract for that? And we're going to put that step on hold for now because we want to really do 3. We want to set up this equation with the parameters to express that as a single variable. I really want to stress that step 3 and step 1 are kind of interconnected, right? So our ultimate goal here is to somehow express L in terms of x. We want to know how to do that. And in order to do that, we have to extract relationships from this. So maybe pause the video if you can and tell me, I'm going to give you a hint, there's 3 of them. What are 3 relationships that you can extract from this little scenario that you're given, from your initial conditions? Okay, so the 3 relationships are all 3 triangles, and I should have, shame on me for not denoting these things as right triangles. My physics teacher would get very pissed at me for making the assumption from this, but this is math and mathematics. We make all kinds of assumptions. So there are 3 triangles from this, and those 3 relationships are the right triangle up here at the top, the relationship between k and z. If you notice that this k is the length here, and then therefore down here this is x, well, this has to be k minus x, x being the hypotenuse here, and then for this height, we have to use the Pythagorean theorem to solve for that. And then for the middle triangle, we have x, z, and L. Those things are pretty much just given to us. Okay, so our ultimate goal here, remember, is to express L in terms of x, because we want to know what value for x will make L as small as possible. Put back our steps here, right? Express this as a single variable. Well, we can see from this, just kind of a given, L appears in one of these triangles. So let's just, if we were to, arithmetically solve for L using the Pythagorean theorem, we would know that L is equal to x squared plus z squared. Okay, so now all that we need to do in order to express L in terms of x is try to find a way to express z in terms of x. So maybe you can do that from this, and if you know how to do that already, great. If not, that's basically what I'm going to be spending the next couple of minutes doing, just working out the arithmetic. So because we have Euclidean geometry that we're assuming here, Euclidean geometry, I think, scales in proportionality in a very linear way. And that's just a fancy way for saying that if you have one triangle, you can say that that's proportional to another. So you may want to notice from this that both z and x in these two triangles, those are hypotenuses. Those are equivalent relationships there. All right, so we're going to say that z is equal to x. Now let's look at what we're given for this one here. Well, we're given a height, right? So we got to use the height from this relationship, which is going to be that. So the height for the z triangle here is k. That's given. And then the height for this is just simply this square root of x minus k, kx squared here. And I'm going to do some basic arithmetic to kind of clean this up, right? We notice that this is k minus x squared here. So if we kind of multiply k minus x times k minus x, that does, k's and x look really similar on paper. Probably should have used different things there. So this is going to be k times k, which is going to give us k squared. This is going to give us kx, and kx is going to give us negative 2kx. And then the last thing is going to be negative x times negative x, which is just positive x squared. Noticing that there is a negative sign out front there, and then there's the x squared there. So let's go ahead and just take that down here. X squared minus k squared minus 2kx plus x squared. If I distribute the negative into that, well, I'm going to get x squared minus x squared minus k squared plus 2kx from there. And so therefore, if we want to just kind of finish out this process here, we're going to say we still haven't done anything to the radical, to the root there. So this is going to be just 2kx minus k squared. Okay, so let's not forget the forest for the trees here. Our ultimate goal is to set this up as an equation to an expression of a single variable. We have L is equal, we've defined L, right, as x squared plus z squared from the initial conditions that were given. We want to define L in terms of x, and in order to do that, we had to set up our proportionality. And now we're going to try to express z in terms of x, and that's going to require us to simply just cross multiply this. And I'm going to do that on the next page there. But let's just go ahead and rewrite what we have so far for L. So L so far in this problem is equal to x squared plus z. We already know what z is, and we're going to express that as z squared, right? So this is going to be kx, because we move that across there, divided by the square root of 2kx minus k squared. This whole thing squared, right? We're just substituting z from this first equation there. Okay, so z by itself is equal to this, and so therefore z squared is that. All right, that's where we're going to stop for this sheet of paper, and we're going to probably move on from that. I'm just going to flip it. I'm a very conservative for the paper. I feel empathy for the trees. Okay, so again, we just solved that L is equal to the square root of x squared plus kx over the square root of 2kx minus k squared. We said that whole thing is squared. This is where we're at so far. Again, from our initial thing, don't lose sight of what we're talking about here. We want to set up L and express L in terms of x. Okay, so let's just do some cleaning up. And so this is kind of a difficult problem, not just because it's difficult as an optimization problem, but it's because it's a difficult in terms of setting things up. So let's clean this up, right? How are we going to clean this process up? Well, we're going to have to do some... The first thing we're going to have to do is just kind of solve for this part here, obviously. So if we distribute that 2 squared into this, we're going to get k squared x squared over square root squared. This is just going to become 2kx minus k squared. Okay, and so let's use this as an example of how to maybe improve our basic algebra, because a lot of people who take calculus don't have a super strong foundation in algebra. That's okay. we also have this x squared here. What is our next step going to be for this process here? Well, my initial first thing I want to do is I want to simplify this expression here, right? I want to maybe do some factoring. Factoring will always save you an extra step or two. So let's factor this one out here. I see that this has a k, this has a k, this has a k. I can probably factor out the k's. So if I factor out my k, I get k x squared over k 2x minus k. And from there, those two k's will cancel out. Still left with that, still left with this. Let's combine those two things together. That gets me x squared plus kx squared over 2x minus k. What's our next step? Well, our next step is to set them equal to the same common denominator. In this case, that's going to have to be 2x minus k. All right, so we're not going to really do any extensive changes to the right-hand side here. This is still just going to be kx squared. But this x squared here, this is going to have to be multiplied by 2x minus k on top and on bottom to set that equal to there. So whenever I distribute this, I'm going to get 2x to the third, and I'm going to get negative kx squared. And I can see just kind of from doing that single step there, that these two numbers are going to kind of obliterate each other, and that gives me a kind of cleaned up version of still just defining L here, being equal to the square root of 2x to the third over 2x minus k. That's just cleaning up there. Okay, so we've cleaned this up pretty much as we can. We've expressed L in as much x as we possibly can. We still have that k there, and so once you've kind of reduced your expression down to as much as you can, trying to follow through with step 3, you do kind of have to at some point leave things abstract. We can certainly represent x not only in terms of, or represent L not only in terms of x, but also represent x in terms of k. And that's kind of the part, again, that makes this stuff really, really frustrating. The next step that we've done, I mean, that's pretty much the difficult part of an optimization problem, is to set it up. From here on out, it's pretty much just deriving for your max and your min. And in order to do that, we just have to use the chain rule, and then obviously we're going to have to use the quotient rule. So if you know how to do this stuff, feel free to skip ahead. It's just going to be me working out the arithmetic. So L prime is going to be equal to square root. Well, I can just go ahead and say that that's the same thing as being raised to a half power. So 1/2 minus 1, that's going to give me negative 1/2 power. That's the first step. And now I need to multiply this using the chain rule. So I'm just going to go ahead. I always have to label my f and my g. So my f, in this case, is 2x to the third. My g is 2x minus k. I'm going to take the derivative of f using the chain rule. So this is going to be 6x squared times, I'll just go ahead and write that out, f derivative times g minus g derivative times f over g squared. I'm doing the inside here. So 6x squared times g, which is just 2x minus k, minus g derivative, well, k derivative is just k to the 0th power, which that just basically becomes nothing. Because that's not we're not deriving with respect to k, I guess is the point that I'm making here. And then 2x is what raised to the first power. That's just going to become 2. So we're going to say 2 times f, which is just 2x to the third. And we're going to divide this whole thing by g squared, which we haven't changed. 2x minus k squared. Okay. So I like to do these things like one at a time and break them down in each. And I'm going to start with the left-hand side just because that's the way that my brain works. So we have something raised to a negative power. That tells us that we have to flip the signs that we're working with here. So we're going to go ahead and just rewrite this whole thing out. 1/2 times, I'm going to flip this, 2x minus k over 2x to the third. And this is still raised to the half power. I haven't gotten rid of the 1/2 yet. And then I'm going to kind of just stop there, and I'm going to go to this side here. So when we distribute this 6x squared into the 2xk, and obviously if we multiply this together, we're going to get 4x to the third. 6 times 2, that's 12. X to the third minus 6 times negative k is going to be negative 6x squared k, negative 4x to the third. Now I'm going to combine my like terms here. I know that they have that in common. This is going to give me 8x to the third minus 6x squared of k. I'm ignoring the denominator at this point, but I'm not forgetting about it because, oh my goodness, that's a problem. You don't want to make those mistakes. Okay, next I notice that they both have an x and they're an even number there, so I can factor out at least a 2x, and I'm going to make that a 2x squared. And from there, I'm going to get 4x minus 3k. And I'm going to divide that by 2x minus k squared, right? Because I'm not done with, I didn't forget about my denominator there. Okay, and I'm going to go ahead and bring this back over here. So 1/2 2x minus k over 2x to the third, whole thing being raised to the 1/2 power. Okay, so this is where we're at so far. I'm going to go ahead and just move this up here, maybe move it off to the side. I'll rewrite it so that I can show my steps here. And we're still saying that this is L prime. 1/2 2x minus k over 2x to the third. I'll put that in its own parentheses there. 1/2 2x x minus, that should be 3k over 2x minus k squared. And some people like to use u substitutions at this step. I don't really mind doing that, but it's kind of just up to you. I'm not using a u substitution that we're using a derivative of it. We're just using that as a variable. But let's just go ahead and first, ignoring or remembering our order of operations, let's go ahead and just distribute that 1/2 into there. So, and you can see kind of just from the get-go, 2 and 2 are going to cancel out there. So we don't have to worry about that right now. So 2x minus k to the 1/2 power over 2x to the third, and I'm going to leave that there as that to the 1/2 power, times 4x minus 3k over 2x minus k to the second power. And obviously we can cancel these two terms out. This is a 2x to the minus k, so I'm just going to get rid of that. And this is 2, right, into the 1/2, so 2 minus 1/2 is 2.5, or rather we could say 3/2. All right. Oh, I made a minor arithmetic mistake here. So this is 2x squared. That should be 2x squared, 4x minus 3, 2x minus k squared. So should really have clarified that. X squared there. We're all right there. Okay, cool. So we've already cleaned up the 2x minus k. Let's rewrite our answer. Okay, so this is our simplified answer that we have so far. We could leave it as this, but if you notice, these both have an x in common. And so if you wanted to, you could distribute that out. And I'm going to see, I'm just going to rewrite them as equivalent because I don't think that they don't help superbly much at that point for understanding the critical values. But for the sake of just kind of simplifying things, it's sometimes helpful. I'm going to go ahead and just distribute it as that, and that's going to be kind of the route that I'm going to take. Yes, you can simplify these x's and distribute that into the 3/2 over 2. I'm not going to do it because I don't think it's helpful for optimization problems to do that. So this is going to give us the square root of 2, x to the 3/2. Again, I'm going to restate this. You can simplify those out if you want to, but I don't know, something about seeing square roots. It's not the most helpful thing, I think, for optimization. Okay, so we have now solved for L prime. So in order to do optimization, the next step, kind of just a routine procedure, what are the values for x that are going to make L prime undefined? Well, we can just do some basic arithmetic, right? Anything that makes this a division of 0, or in general, is going to be that. So obviously, we can say that if x equals 0, therefore L prime would be undefined. That's the first thing that we can say. But if you remember from our problem at the beginning of this, that's a length of x. That's a physical length of x. X's length in this can't physically be equal to 0 for this type of problem. So since it's physically impossible, we're just going to omit x equals 0 as 1. Okay, what else is a critical value that we could get from this that's going to make x equal to 0? Well, let's go ahead and solve for the denominator here. So 2x minus k. If this is equal to 0, then obviously that's going to give you a 0 in your answer there. So we add k to both sides. X is going to be equal to k over 2. That's one of them. The last critical value you have for that is going to be just the 4x minus 3k, setting that equal to 0. So 4x is equal to 3k. We're going to simply say that x is equal to 3/4 of k. At this point, we've identified the critical values. We've omitted one because of the conditions that were given. Now what we have to do is just kind of follow along with the procedure. And I think different people have different ways of doing this procedure. I like Patrick JMT's way of doing it. And basically, you just look at the critical values that we're working with. So the first critical value is 1/2 of k. The other critical value is 3/4 of k. And these are values for x that we're talking about here, right? So if x is, let's say a number that's less than 1/2 of k, I will use, 1/4 of k. If x is 1/4 of k, 1/4 of k would be just 1/4 times 2/4. That's going to be 1/2. We're subtracting that from k, and then we're taking it to the 3 squared. That's the same thing as saying that we're going to cube that number, which will be negative, and then try to take the square root of it. See, and you can't take a square root of a negative number there. So I know automatically that this will be undefined over that ratio there. So let's move on. Let's pick a number between 1/2 k and 3/4 k. I'll say, 2/3 of k. Well, 2/3 of k, top value, 2/3 times 4. Let's see if that's going to give me 8/3, which is certainly a fairly large number there. So let's do 2/3 times 4 gives me 2.667. And if I subtract that from 3, that's going to give me a negative number up top. On the bottom, though, I believe 2/3 times 2. Let's see, 2/3 times 2 is going to give me a number greater than 1. So this will be negative up top, positive on the bottom. Therefore, this is going to be a negative value, right? You're decreasing over that interval there. Okay, let's pick a number that is greater than 3/4 of that. I'm just going to say that it's equal to k. Right? So if x is equal to k, this becomes 4k, which is positive. 2k minus k is still going to be positive values there. So it's going to be positive, and therefore it's going to be increasing over this interval. And we're going to take note that we went from decreasing to increasing. So this is a absolute min value there. And that was kind of what the question is. Remember, we wanted to know what the value was for x that made x equals what in order for L to be as small as possible. Well, in this case, 3/4 of k.